So, hello everyone, how are you all? I hope you all are fine and safe. Well, again, welcome back to Quantum Mathematics. I'm Aman, just welcoming you all to a new amazing video in which we are going to talk about a crazy integral. Like the integral which we are going to deal with today is really amazing. And if we go further in it, like I'm talking about a successive version of that integral or the integrand that we're going to propose today, oh, that's going to be, that is literally just going to be crazy and crazy and crazy. When you just add this up. Actually, the integrand for our today's video is a tetration. You know what tetration means? Basically, let's talk about a tetration, right? Tetration. Although I haven't talked about this tetration yet, but let's talk about this now. So basically, it's a form of like, look, we know about we know about 2 to the 3, right? It's called exponents, right? 2 to the power 3, right? So that is basically you have to multiply 2 3 times, like 2 times 2 times 2, which comes out to be 8, right? But if we talk about the representation of tetration, so if we talk about the third tetration of 2, so third iteration of 2 would be represented as this, something like that. Look at the difference. I'll tell you what's that gonna give us, but look at the difference between the notation or the expression or the representation of both these things. So it's 2 to the power 3, and the 3 would be written something like that on the upper side and on the right hand side, right? But for tetracon we have to write the thing like we are talking about the third tetracon. So basically that is 2 to the 2 to the 2. Just look at the difference. We are talking about 2 to the cube. That means we have to multiply 2 3 times, like 2 times 2 times 2, which comes out to be 8, right? But we have to we have to take exponents 3 times of 2. So basically that's gonna give us, it's 2 to the 2, that means 2 to the 4, and that is 16, right? So if we talk about the fifth tetracon of 2, so that is going to be crazy because 2 to the 2 to the 2 to the 2 to the 2. So you can compute that by your own because it doesn't look simple at all, because it comes out to be 2 to the 4 to the 4, which is 2 to the 16, right? Oh, yeah. But if we talk about 2 to the 5th, so it's just 32. So you can just look at the difference between 2 to the 16 and 32. So yeah, that's crazy. So that is what we are basically we are just going to talk about in today's video, but in an integral form, right? Okay, let me just write down the integral that we are going to deal with today, right? Because yeah, I think tetration is clear to you all, guys. It's not difficult to understand at all. It's just a representation, I think. Yeah. So basically, I would say I equals integral from 0 to 1 of x to the x dx. So this is what. And you know what? The integrand is x to the x. So I can see it, the x to the exponents of x, maybe because x to the, like, x is an exponents, right? So I can say x to the x exponents, or maybe I would say that first iteration of x, right? Or maybe we should say if we talk about x to the x to the x, so this is the third iteration, right? And it's the second iteration. So this can be written as this, something like that. Oh, I think, oh no, it's 3. Yeah, that's pretty fine. And this is x to the x can be written as something like this, right? Okay, so this is what we are here having. This is what we are having today. So I think we should begin, right? Well, you don't need to care about tetration, right? If you're not comfortable with that, just leave it. Let's talk about this only, right? But although I just explained you a little bit of that. So if you have watched one of my videos named Sophomore's Dream, let me just write that down here. Sophomore's Dream. So in that video, an integral from 0 to 1 of 1 over x to the x dx evaluated to sum as n goes from 1 to infinity of 1 over n to the n. So, like, this was a crazy video, I think, and this is literally beast, because the proof we began was something we had introduced something crazy, and I told you to remember the thing that I asked you to remember in that video. So if you haven't watched that video yet, please watch that video, because I have explained a lot of things in detail. So basically, it's the negative fraction or the negative power of x. Like, we can write this as x to the negative x, right? So yeah, it's something sort of like that. But we are talking about the numerator only. We are not getting into denominator, right? Okay, so now this is being crazy. Because we are talking about this one and we have already talked about this one. So yeah, that's pretty good. So now let's just prove this stuff. Okay, so in that video, in this Sophomore's Dream, I requested you to remember that if we have something like this, so we can write this as e to the ln, something like this. So yeah, it is something like, or anything, it could be anything. So for our case, let me just consider x to the x. So this is x to the x. So x to the x can also be written as e to the ln x to the x. And from the basics rules of natural logarithm, so we can say it's e to the x times ln x, right? And again, we have talked about a lot the Taylor series of e to the x. So let's just introduce here. So e to the x equals the sum as n goes from 0 to infinity of x to the n over n factorial, right? Okay, so for our case, x is x ln x, or I think I should consider z here. So yeah, so for our case, z equals x ln x, right? So e to the x ln x is gonna be the sum as n goes from 0 to infinity of x to the n ln to the n ln to the n ln x to the n over n factorial. So this is what we are having after using the Taylor expansion of a to the z, and this like amazing way to introduce anything in terms of an infinite series. Like, the thing that I have written on this board is really important, and I would recommend you to just write it down, right? Okay, so now let's just plug this infinite sum over here, because we know that e to the x ln x equals x to the x. So basically, x to the x equals the sum, so we can just replace x to the x here with the sum. So our I is gonna be integral from 0 to 1. The sum as n goes from 0 to infinity of, we are having x to the n ln to the n x over n factorial dx. Since the sum, we can, due to linearity, we can just switch the order of integral and this sum, as well as we can just plug out this n factorial since it's not depending on x. So the sum as n goes from 0 to infinity of 1 over n factorial, and integral from 0 to 1 of x to the n ln x to the n dx. Now we are done with this part, right? But we have to care about this thing. So let's consider this as, j, right? So let's just consider that integral j, and let's talk about that a little bit here. So if we talk about j here, let me just check whether this line is visible to you or not. Yeah, it's visible, right? Okay. So basically our j is integral from 0 to 1 of x to the n ln to the nx dx. So we are using u sub here. So let's say that x equals e to the negative t, right? Let me just check. I think everything is visible to you. Yeah, it's visible. So I'm just taking an assumption that x equals e to the negative t, right? So if we take the derivative, so dx is gonna be negative e to the negative dt. So dx is gonna be negative e to the negative t dt, right? And yeah, so our j is becomes, and if we talk about limits, so let's talk about limits here as well. So if you plug x equals 0, so e to the negative infinity always gives 0, right? So basically t would be infinity, right? So for x equals 0, t equals infinity, right? And for x equals 1, t would be 0. So basically our j is gonna be integral from infinity to 0, right? And we are having x is being replaced with e to the t, e to the negative t. So e to the negative t to the n, right? And ln of x to the n. So ln of x means ln of e to the negative t. So basically that is negative t to the n, and we are having e to the negative t dt. I'm sorry, negative. Oh, wait a second. Negative e to the negative t dt. So this is what we are having as the derivative factor. Now, this negative is gonna help us to just like replace or maybe interchange or maybe just switch up the order of the limits, because that is an improper integral, right? So let's talk about that here. Okay, so basically our j here is integral from 0 to infinity, right? Wait a second, it's infinity, right? And we are having e to the negative n t and e to the negative t as well, this one. And we have used this negative to just switch up the order of the limits, right? And we are having, well, we can just write this as negative 1 to the t and ln to the, oh, I'm sorry, t to the, oh, negative 1 to the n and t to the n dt, right? Okay, now I'm just going to combine this these e terms, and I'm just going to plug this negative 1 to the n out of the integral. So j equals negative 1 to the n integral from 0 to infinity of t to the, well, I can just write this as t to the n minus 1, I'm sorry, plus 1 and minus 1, right? Why I'm doing that, just wait for that moment. So I've just added 1 and subtracted 1 as well in the exponents of t. Okay, and for e, it's gonna be negative n plus 1 t dt. Now, let me just remind you something here, and obviously have talked about this a lot of times in our earlier videos. Even I have uploaded the introductory part on this as well. So basically, identity integral from 0 to infinity of t to the z minus 1 e to the negative a t dt. Since where z and a are constants, right? So, and maybe z is greater than 1, or maybe greater than or equal to 1, actually greater than 0, I would say. And so that's gonna give us gamma of z over a to the z. So again, a basic identity. Well, you can just prove that down by your own. It's not difficult to prove it here, but I'm not gonna prove this down here in this video because that's gonna take time. So for if you want the proof, so we can you can just consider asking me in the comment section. I'll definitely just upload a proof of that. So let's just use that here. So for our case, z equals, look, z equals n plus 1, right? And a equals, oh, yeah, a equals n plus 1 as well. So basically we are having j equals negative 1 to the n and gamma of n plus 1 over a equals n plus 1 to the n plus 1, because z equals n plus 1 as well, right? Okay, it's redefined, right? So now, well, we can just write this as j equals -1 to the n times n factorial over n plus 1 to the n plus 1 as well, since gamma of n plus 1 can be written as n factorial. So now let's just replace this j with this result that we have computed so far. So I equals the sum as n goes from 0 to infinity of 1 over n factorial -1 to the n times n factorial over n plus 1 to the n plus 1. And we can see this n factorial and n factorial getting cancelled out successfully. So basically we're having I equals the sum as n goes from 0 to infinity of -1 to the n over n plus 1 to the n plus 1. Or maybe I can write this as I can just write this as I equals the sum as n goes from 1, not from 0, right? So I have to just add a plus 1. Well, look, wait a second. I have to explain it to you now. -1 to the n plus 1 equals -1 to the n minus 1. This is really crazy. So if I'm beginning our sum from n equals 0, so that's gonna be -1, n equals 1, I'm sorry. So that's gonna be -1 to the n minus 1 over n to the n. Or I can write this as n plus 1 as well. So this is the final result for our integral. Wow, that's really amazing. And it wasn't that difficult to evaluate. We just have to play with some Taylor expansions and some this identity. So from these stuffs we can easily prove that down. And I'm thinking to just come up with the successive order of this of the integrand, that is x to the x to the x. That basically means the third iteration of x as an integrand with the integral from 0 to 1. And you know what? We are having a single sum here, right? But if we talk about this, the successive order, so we would be having double sum. And if we talk about the another successive order, that is another far. So that's gonna give us the third sum. So this is amazing. And if I talk about the infinite iterations, so that's gonna give us infinite sum of sums. This is really hard to digest. Okay, now I think we should just cut off, and I think again guys, if you got to learn something from this video, make sure to like, subscribe and share. And if you have any kind of doubt, you are free to ask me in the comment section. I'll make sure to reply that as fast as possible. And yeah, I think goodbye, love you guys, take care, and stay tuned for the next video, because I'm just gonna bring a lot of things for you. Whoa, goodbye guys.